We've been talking about eliminations. That's like the first thing you cover when you take an introductory organic chemistry course is substitution and eliminations. SN1, SN2, E1, and E2 elimination reactions. So that's what we're talking about here is how do you make CC double bonds, mostly CC double bonds, by pulling off a proton and then eliminating something out to make a pi bond. And we're mostly focusing in this section on CC pi bonds. But that's not exclusively what we're talking about. Okay, let's go ahead and talk about, when we left off, I was showing you some elimination mechanism that goes through something called the E1 conjugate base. This is one of 3 types of elimination mechanisms. There's E1, where you make a carbocation and then pull a proton off. There's E2, where you deprotonate and push out the leaving group. And then there's E1 conjugate base, E1CB. This is usually the last thing they teach you in a sophomore organic chemistry course, but it is the most common elimination mechanism, unfortunately. They give you the least amount of practice with the most common elimination mechanism. It requires that you understand how to stabilize an anion, usually a carbanion. So in these cases over here, we're talking about you have to find some system where you can stabilize a carbanion. CH next to a carbonyl is most common. But you could have a CH next to a nitro group, next to a cyano group, something that can stabilize a carbanion. And I showed you this wacky case of FMOC deproduction where you can deprotonate at this space to make an aromatic fulvene or type system that's aromatic in the middle, and that carbanion then pushes out the leaving group. E1 conjugate base, you make some sort of an anion, and then the anion, C minus, O minus, N minus, pushes out the leaving group from next door. Let's talk about another mechanism, the one that should be more familiar to you, and that is an E1 elimination mechanism. E1, you're going to make a carbocation, a carbenium ion. It's like, once you make that carbenium ion, are you going to add and do SN1, or are you going to pull off a proton and do E1? Well, it depends on what you have in solution. So here's a pretty typical case of an E1 elimination mechanism to make a CC bond. And you can see the stuff that's in here. In this mixture, we've got a tertiary alcohol next to an aromatic ring. And so that's going to make it very easy to make the leaving group leave. This is under acidic conditions. And then, and after we make that leaving group leave, we'll have a carbocation. So let's go ahead and take a look at this. So, right, if we have some sort of a proton source, I'm not going to draw the arrow pushing mechanism for protonation of that OH group, but I think you get the idea that if you're in toluene sulfonic acid, that's about as powerful as sulfuric acid, that you're going to protonate that to make this oxonium ion. This water is ready to act as a leaving group, and that's just going to act as a leaving group. How do you know? Because tertiary carbocations are favorable. And this isn't going to be just a tertiary carbocation, it's also benzylic. So the carbocation, the resulting carbocation, is going to be stabilized by resonance with the aromatic ring, pi resonance, and it's tertiary. So that should be favorable. Forming tertiary carbocations, you should know to do that. Now that carbocation has 2 choices. You can add nucleophiles in there if you've got decent nucleophiles, or you can pull off a proton from next door. Let me pull off that proton, or draw that proton that's next door. There it is. And there's another one on the other side that's identical by symmetry, that's indistinguishable by symmetry. Now what types of nucleophiles would add in? Chloride. But you notice we were very careful not to use HCl in this reaction because we don't want chloride to add back in there. Right? Toluene sulfonate is not a good nucleophile. It pops out as soon as it adds in. So what would be another nucleophile? Water, right? We're not running this reaction in water. You would typically run it in something that's innocuous, some chlorinated solvent or something, but you wouldn't run it in water or an alcohol solvent because you don't want water or alcohol to add back in. So under these circumstances, because the tosylate is not a good nucleophile, you don't have a decent nucleophile in here, what happens is that you're simply going to pull off a proton from next door, and that's going to lead to an elimination. So E1 mechanism goes through a carbocation. You're looking for stable carbocations. Can I form a stable carbocation? Cyclopropyl carbocation, something that is stabilized, or a benzylic or allylic carbocation. Now you've seen lots of E1 mechanisms. Not through carbenium ions, like traditional carbenium ions. Let me show you the most common E1 elimination mechanism that you would have seen. And that is when you're doing acetal chemistry and aminal type chemistry, and iminium ion type chemistry, you're usually protonating some sort of an oxygen leaving group and having it leave to generate a carbocation. Let me go ahead and draw an intermediate. If this was under acidic conditions, look at all those oxygens on a single carbon. See all these oxygens? They're all trying to push each other out. And the second you protonate one of these with some sort of a catalytic acid, one of those other oxygens is just waiting there to push out that water leaving group. You can't stop that from happening. It's just going to leave here. Watch this. I'm going to make a carbocation intermediate, and I'll end up with this carbocation intermediate that's wonderfully stabilized here. So, I mean, it's a well-stabilized carbocation intermediate, just like up above, except this is even more stable than the carbocation above. Those lone pairs on the oxygens are doing a better job of stabilizing that carbenium ion than that naphthalene ring up on top. Now I could draw another resonance structure for this, another resonance structure that's actually a better resonance structure. I can use the lone pairs on either one of those oxygens, I'll use the hydroxy group, and depict this in a different way. I'll depict this same carbocation with a different resonance structure. Here's the same carbocation. Like that. And you can kind of see the last step of this mechanism is we're simply going to deprotonate this using our whatever the conjugate base is left over from our acid. So this is a more common elimination version of E1, is to make C double bond O instead of C double bond C. Now I mentioned that there was another way you could have depicted this. I kind of hinted at that. It would probably be better, I would love it, if instead you depicted it like this. Don't just make the water leave, push out that water. That's why that water's leaving so quickly. And up above here, why is that water leaving so quickly? It's because the pi electrons are helping to push that out. Right? It's not just that the stabilizing groups are there in the carbenium ion. Those groups were there pushing out the leaving group in the starting material, right, before you made a carbenium ion. So, right, this kind of arrow pushing mechanism would take you directly, right, if you use these lone pairs, that would take you directly to this second resonance structure. Either one of these resonance structures is fine, but I hope you can see that lone pairs can push out leaving groups. Lone pairs can push out leaving groups. Get used to that. So E1 is super common, not for making alkenes, but for making C double bond O. And you might not have recognized that those were E1 mechanisms when you did acetal type chemistry. Now sometimes you don't have, you can't make a stable carbocation. There's going to be times when you like this case over here where, down below, where you just can't make a stable carbocation here, like that would be a secondary carbocation. That's a good leaving group. That's kind of like a tosylate. We call it a benzene sulfonate leaving group. That's a great leaving group, but if you make that pop out, you're going to get this secondary carbocation that's not good. Now, fortunately, we have a strong base under these conditions. We have a powerful base. So what happens if we can't form a stable carbanion here? So we've added a strong base here, and I'll just put RO minus. We put a strong base in here, but we can't just deprotonate and make a carbanion here. There's nothing to stabilize a carbanion there. You can't just pull a proton off and have CH2 minus. There is no base that can do that. But if we push out the leaving group as we deprotonate, if we draw that proton there, we can do these in a concerted fashion. We can't make a stable carbanion, we can't make a stable carbocation, but if you have a strong base and a great leaving group, that combination allows us to do an E2 elimination, a concerted elimination. Not very common, not very easy. Boy, there's all kinds of entropic requirements here. Everything has to be perfectly aligned. Very few alkoxides collide with that substrate with perfect alignment. Most of the collisions are not successful. E2 eliminations are hard. This is the most common mechanism that you're going to draw for every elimination because it's the fewest number of steps. And you're usually wrong when you write a concerted E2 elimination mechanism. You probably should have been drawing an E1 conjugate base, or maybe you should have been drawing some sort of right up here. You don't deprotonate at the same time that you're pushing out the leaving group up here. You do those in separate steps. So E2 is the least common of these mechanisms. So let's talk about, see if we can talk a little bit more about E2 and what are the requirements for E2. It's not easy. You gotta have you gotta meet special requirements in order to satisfy that E2 stuff. All right, so I don't know if I feel like I need to draw this out, but E2, the E2 elimination mechanism requires a perfect anti-relationship. Well, it works best when you have a perfect anti-relationship between the proton you're taking off and the leaving group. And that's because you want the electrons in this HC bond right here to be aligned with the antibonding orbital for the CX bond. Right? There's this antibonding orbital for the CX bond that's sticking back here, sigma star CX. And the only time you're going to get, well, not the only time, the best way to get great alignment with the electrons in this CH bond is if those two bonds are anti to each other and parallel. And we refer to that as anti-periplanar. That arrangement is referred to as anti-periplanar. So you want those groups to be anti to each other. Now, it is true, right, if I draw the antibonding orbital over here for this CX bond in this arrangement, right, there is a little bit of overlap between the sigma star orbital here, sigma star, right? There's a little bit of electron density for sigma star HC. I can't fit the HC in there. For that HC, when there's exactly a syn arrangement, when the HC bond is exactly syn to the CX bond. But that's not equally good because the back end of this sigma star orbital is not very big. So you won't get as efficient elimination if it's exactly syn. You'll get the best, fastest elimination if the HC bond over here is exactly anti and parallel to the CX bond with the leaving group. That's going to be the best arrangement. And we know something about the relative rates of these processes. You know, the rates for the anti-elimination versus the syn, they're almost always hundreds in terms of times faster. But I'm just going to give you a more conservative estimate here, that it's usually 10 times faster. More than 10, it is more than 10 times faster when you have that anti-arrangement. So molecules that can adopt that anti-periplanar relationship are going to do that. Let's take a look at a conformationally restricted example where you don't get to rotate around the bonds and explore conformational space. Here's down below here, here's two different cyclohexyl bromides. But in one case, the bromide is going to be locked in this axial position over here because the T-butyl always wants to be equatorial. And in the other isomer, the trans isomer, the carbon-bromine bond is going to be equatorial. Pretty much all the time, because there's no way you want to flip the chair in either of these to put the T-butyl axial. T-butyl is always going to be equatorial. So if we want to do an elimination, we need to look at the protons that are beta to that carbon-bromine bond. Let me go ahead and draw it perfectly, paying attention to all the correct conformations of the substituents here. So if I draw the H's, I don't really care about the H next to that bromine, but I think it'll help us to draw it. What I care about is these, let me draw them in blue. I care about these H's over here. I'll draw them in the dark blue, so it's hard for you to see. I'm going to draw those H's that are beta to the HBr. And there's only one CH bond over here that is anti to the carbon-bromine bond. There's only one HC bond that you can deprotonate in order to push out that leaving group. Now, sometimes it is hard for people to envision these anti-periplanar relationships, and so we oftentimes use something called a Newman projection to really reveal and emphasize anti-periplanar relationships. Right? For eliminations that are concerted, E2, we care about anti-periplanar relationships, and so we sometimes use these Newman projections. And the idea behind a Newman projection would be if you were to stand, if you were to sit right here with your eyeball, it's like a naked eyeball right there, and stare down that bond, what would you see? What would you see if you could stare down that bond down this CC axis? What's the arrangement of groups that you would see? Well, the carbon closest to our eyeball right there would have this cyclohexyl ring here and would have one H that's equatorial and one H that is straight down axial. Let me draw those in blue just because the way my Newman projection will match the fantastic colors I have there. So that front carbon that's closest to our eyeball is going to have one H equatorial and one H pointing straight down axial. And if I could envision the hidden carbon that's in the back here, this carbon that's in the back, and put the substituents, well, there's a carbon-bromine bond sticking straight up. Let me go ahead and draw that long bond back there. There's that carbon-bromine bond sticking straight up. Equatorial, there's an H, and then at this other position down here, we're going to have the other part of the ring, the R group. So when I look at this, I can see that this first substrate here has a great arrangement, a great anti-paraplanar relationship between these two bonds. This HC bond here is anti to the carbon-bromine leaving group, and so we have a great arrangement for a rapid E2 elimination reaction. Now, if I try to do the same thing over here for this other alkyl bromide, let me go ahead and draw these key substituents on here. I'll draw the H next to the bromine, even though that's not eliminating. But on this beta carbon, there's an H that's going down, and there's an H that's equatorial. And so when I draw those substituents on there, the R and the bromine and the H that's on this in back that's on the same carbon as the bromine, those two blue H atoms, I guess I didn't draw them in blue. Let me try to trace over that in blue. Those two same blue H atoms, neither one of those HC bonds in blue is anti-paraplanar to the carbon-bromine. We're kind of screwed. Neither one of those has a great relationship. So you should not be surprised to find out that one of these reacts. The relative rates for an elimination using T-butoxide, that's hindered. It's hard to do SN2 with T-butoxide, is about 500 to 1. It's kind of amazing that you get any elimination from the equatorial bromide. But that anti-relationship is so well enforced in that first isomer that you get a vastly faster rate when you're locked into a situation where you have a locked-in anti-paraplanar relationship. So sometimes Newman projections will help you see those relationships, and again, you're just kind of there's no HC that is anti-paraplanar to this carbon-bromine. The only thing that's anti-paraplanar is the carbon bonds in this the carbon-carbon bonds in this cyclohexane ring, and you're not going to deprotonate a carbon, pull off a carbon. Well, we'll show you how to do that shortly, actually, a little bit trickier. All right, so E2 eliminations, that anti-paraplanar requirement for a fast E2 is hard to achieve. It takes, the base has to collide at just the right angle when it's in just the right conformation. Here's a case where you don't have a locked-in conformation. So here's a case where you can rotate any way you want, and this molecule is going to have every possible rotamer floating around in solution. This is like stat mech. There's 10 to the 23rd molecules. It's a whole population. Some exist in one conformation, some exist in the other. The way you're going to get elimination is when these molecules just happen to be in a conformation where the X group, like this, I'll draw the X group pointing up here, where the X group is anti to one of the protons. This thing can exist in all different types of conformations. And there's nothing stopping this substrate from putting the R1, like if you were to stand here and look down this bond axis, there's nothing stopping this from adopting a conformation where one of these two H's on the front carbon is anti to the X group. Now, that may look fine, but look at these two R groups over here. If I put it into this conformation, I'm going to have this painful steric interaction between those two alkyl groups. That's not the preferred conformation for an E2 elimination. There's another way that bond can rotate around and place an H anti. It's if we rotated this around so that this other H was down here, right? If we rotate this like this, we can put the other H atom anti to the leaving group X. And that's going to be the preferred conformation for elimination. And when we adopt that conformation prior to the E2 reaction, it's going to put the two R groups on opposite sides. And that relationship will be maintained in the product. Those two R groups will end up on the opposite side of the double bond. If you just have a long chain with a bromine or a chlorine in there and you do an E2 elimination, you're going to get a trans double bond. Because in the transition state, you want the R groups to be far away from each other in the transition state, so they end up far away from each other when they make the alkene product. So we would refer to this as stereoselectivity. That's called stereoselective when you have a reaction that favors one stereoisomer. Doesn't matter why, but if you have a reaction that favors either cis over trans or trans over cis or erythro over 3O. I don't know if you learned that nomenclature. Or one diastereomer over another. We call that a stereoselective reaction. Now I'm going to show you another term that we're not going to use in this class, but it's different, and if you hear it, make sure you don't confuse it with stereoselective. There's another very special term that we use when we talk about stereochemistry, and that's stereospecific. A stereospecific process means that if you start with one diastereomer of the starting material, you get one diastereomer of the product. If you start with the other diastereomer of the starting material, you get a different diastereomer. That's called stereospecific. And the only way to show that a reaction is stereospecific is if you take both diastereomers of the starting material, you show that they give different diastereomers of a product. So in this case, it could be one diastereomer of the starting materials here, give one E versus Z diastereomer, right? Those are stereoisomers. E versus Z is a different stereoisomer. So let's take an example of this. It's a little bit hard to see. I'd have to assign Con-Ingold Prelog would make it the easiest for us to see. This to me looks like it's the S configuration here, and on this other atom it is 1, 2, 3. That is the, wait, 1, 2, yeah, and that is the S configuration there. And if I quickly assign the configurations on this other one, it's going to be R over here and S over here. Those are diastereomers of each other. You won't be as quick as assigning Con-Ingold Prelog, R and S, but maybe you can just see that those are not the same diastereomer. They're not enantiomers of each other. They're not mirror images. They're diastereomers. And this diastereomer over here on the top, if we do an elimination from that, if we come along with our base, what would we use? Something like T-butoxide, maybe something hindered is what we would want, and strong. And so we would come along and deprotonate that. And as long as it's in this conformation where that H is anti, we can push out the leaving group here. And what I want to make sure is that I maintain this relationship. Once I've drawn the H and the leaving group anti to each other, if the two methyl groups over here were on the same side, right, same side, they're kind of pointing out towards us, they better be on the same side in the product or I've done something wrong, right? They were above the plane of the board with bold bonds in the starting material, they better be on the same side of that alkene when I draw the alkene product. Now, if I come to this other diastereomer over here, the SR diastereomer, and I do the same elimination, putting the H and the leaving group anti and parallel to each other. So I draw my arrow pushing. If I pull that proton off, great overlap, push out the leaving group. Now notice that the methyl here is on the same face as the H. Methyl and H are sticking out of the plane, right? And that's a different diastereomer of the product. So this is a stereospecific process here, that where one diastereomer of the starting material gives the E alkene and the other diastereomer of the starting material gives the Z alkene. That's a stereospecific process. When one diastereomer does one thing, the other diastereomer of the starting material does something else. And you can't tell something is stereospecific until you've tested both different diastereomers. Whereas stereoselective, you just run a reaction and you see one stereoisomer, and it's like, okay, that was stereoselective because I didn't get two stereoisomers in my product. All right, now I've never taught the first quarter of introductory organic chemistry here. It is this hell of SN1 and SN2 and E1 and E2, and they always ask you questions like, oh, here's some secondary alkyl halide. Is it going to undergo E1 or E2 or S? I don't know. But what can you rely on? Here's a piece of gold that you can rely on. When you're comparing substitution versus elimination, you usually get mixtures, right? If you got secondary, maybe if you have tertiary, it's a little easier to decide. But when you've got secondary alkyl halides, or you protonate an alcohol, have a water leaving group on a secondary center, you're usually going to get a mixture of SN2. Even on a primary alkyl halide, you usually get elimination competing, even when there's very little steric hindrance. But one thing you can rely on is that heat usually favors elimination over substitution. If you want more elimination, heat it up. Because the entropic requirements for elimination are much higher. You've got to have all these alignments between CH bonds and empty orbitals. CH bonds have to be aligned with empty p orbitals, or CH bonds have to be aligned with sigma star. That's a high entropic requirement, and there's a temperature dependence to that. So more molecules will have a reactive conformation when there's some sort of a collision as you heat up a system. So let's take a look in practice how that impacts a typical process. So here's a reaction that you couldn't predict what's going to happen here. You take a strong nucleophile, strong base, and a secondary alkyl halide, and you're going to get a mixture of SN2 and E2, right? If it were a primary alkyl halide, you'd get mostly SN2, but this is a little bit more hindered. And you've got all these protons that are beta to this. This strong nucleophile is also a strong base. And so if you look at what happens at room temperature, you don't know anything about rate constants. These rate constants are listed in per molar per second. That shouldn't mean anything to you unless you've looked at a bunch of rate constants. I've looked at enough to know, boy, 10 to the minus 5 or something, that's a slow reaction. You're going to be waiting a while for that thing to finish. But what's nice here is that you get a 1-to-1 ratio. It's about 1 to 1. I mean, I'm not real good with math, but that looks like about 1 to 1. Do I care whether it's 55-45 or 50-50? That's about 1 to 1, right? That's not good. But suppose you're not happy with the slow reaction and you start heating this up. We have a very powerful rule that works most of the time in organic chemistry. Every 10 degrees you raise the temperature, the reaction rate doubles, right? If you want to get done quicker, if you'd like your reaction to be done 8 times quicker, you're going to need to crank up the temperature by about 30 degrees, right? You can do a rough calculation, right? Do I want to be sitting here at midnight when my reaction finishes, or just crank up the heat and get it to finish faster? Do I want to wait 2 weeks for this to finish, or do I want to be done by tomorrow? Right? That's something you control. But you got to be careful with heat, because look what happens as we heat it up. Everything gets faster. SN2 gets faster to do the substitution. E2 gets faster, where you deprotonate here and then knock off the leaving group. They both get faster, but they don't get faster at equal rates. Look what's happening here. The E2 accelerates, gets faster even more than the SN2 gets faster. So in this case, as you're heating it, they both get faster, but you'll end up with a 1-to-2 ratio. Right? The heat is more responsive. The E2 mechanism is more responsive to heat. Yeah.
Out of curiosity, how would you isolate the E2 product if that were your design?
That's a great question. You generally would not isolate the E2. It usually evaporates out because it has no polar groups on it. So in practice, what happens, usually when you do substitution reactions, people say, oh, I got this clean reaction. No, it's not clean. What happens is the alkene that is nonpolar usually evaporates out or comes off when you do rotary evaporation. And people don't see that byproduct. They think their reaction was clean. No, it was dirty. And they're just not seeing the nonpolar volatile byproduct. Now, unfortunately, I don't know any chemist on the planet Earth that wants the elimination product. When we do organic chemistry, we want to assemble bonds, like this one right here. I don't know anybody who wants to break bonds and not form new bonds. Right? And the other side of that, or maybe the same side of that, is you usually make alkyl halides from the alkenes. So if you just finished taking the alkene and converting it into the alkyl bromide, why would you eliminate that back off? Nobody would ever do that. You almost always want the substitution product, and you almost never want the elimination product. So if you want to favor substitution, you got to cool it down. And unfortunately, that usually means waiting longer. So in that case, you'd want to add silver and yank it off, not just heat it up. That's not going to make your, that has other issues. So heat will tend to favor elimination process. It will favor E1 over SN1. It will favor E2 over SN2 as you heat things. And the opposite would be true if you cool. You'd favor the substitution process. Okay, so everything I've been telling you about is anti-paraplanar relationships with HC bonds anti-paraplanar to leaving groups. But let's go away from HC bonds, because that's not everything. We love silicon so much in our upper division class here. Let's take a look at a carbon-silicon bond. Boy, this system just looks like we're trying to make a carbocation there. Can't you imagine how great this would be if we protonated this and then we had this whole thing pop off? You could do that, but that's not traditionally how this protecting group is removed. So why do you use this protecting group? Sometimes you want to carry an amine through a multi-step synthetic sequence, But you don't want that amine lone pair reacting with stuff. So you put a carbonyl next door. You make some kind of a derivative with a carbonyl on the nitrogen, and then you remove that later when you want to use that lone pair for something. So one possible protecting group is called the TEOC protecting group. So it's the trimethylsilylethyl or trimethylsilylethoxy carbonyl protecting group. And usually the way you deprotect these is not using acid, which would make a beta-silocarbocation. You usually deprotect these with fluoride anion. Tetrabutyl ammonium fluoride is the most common. We usually refer to this as TBAF in the lab because, I don't know, it just sounds cooler when you say TBAF. I'm going to draw that fluoride anion over here. And fluoride loves silicon. Oh, man. That is love. That fluoride is going to attack the silicon. And you may think, oh, is it really going to attack and make a siliconate? I've never seen that before. Sure, you've seen siliconates before. Fluoride loves silicon. Man, fluoride loves silicon. We don't buy hydrofluoric acid in glass bottles. It would chew through the glass bottle. That's silicon oxide. So we have to buy HF in plastic bottles. So let me go ahead and draw out this amazing pentacoordinate silicon intermediate here with that marvelous silicon-fluorine bond. There's a siliconate with a negative charge. That's okay. 5 bonds to silicon, no problem. And we still have this carbamate over here. There we go. Now, it's certainly possible that you could pop out the fluoride, but I'm not going to draw that. That just takes us back to starting material. Why would I draw going back to starting material? I'm trying to explain how we get to the products here. And there's another bond here that we can use to break, and that's this silicon-carbon bond right here. Both those axial bonds are nucleophilic, right? All the bonds are nucleophilic, but especially the axial ones. And that bond, when it is aligned, when it rotates around in this conformation, that silicon-carbon bond will be aligned with this antibonding orbital. And it can push that group out. It can push out that O- leaving group. And so that will give you this carbonate intermediate species. I'm not going to draw out all the steps here in this. And then eventually that will lose the carbon dioxide as kind of a driving force here. And then you'll have this unprotected amine you can now take into more reactions and start doing nucleophilic reactions using that amine lone pair. So again, this is an elimination reaction, but instead of an HC bond, we're using a silicon-carbon bond. And let me show you kind of a related variation of this that uses a silicon-carbon bond to make leaving groups leave. And there's 2 different versions of this process, which is called a Peterson olefination. Right here, you're making a pretty boring olefin, which is ethylene gas. Now, we do not need to go through this complex synthesis to make ethylene. We could just buy ethylene if you really wanted it. But sometimes you want to make complex alkenes in the lab, and we want to use silicon-carbon bonds, the elimination of silicon-carbon bonds, to make that happen. So here's one process. One process is to take beta-silanols like this and turn the OH into a leaving group. That's going to make a beta-silocarbocation. Now, you'd think you could just dump in sulfuric acid and make it a leaving group. That's not quite controlled enough. So what they do is they use trifluoroacetic anhydride commonly. I'm not going to show all the steps here to make a trifluoroacetate leaving group. That is not a great leaving group, that trifluoroacetate, but it's good enough here. It's good enough because we got this beta-silo group. It's a good enough leaving group because when we make that leave, we're going to end up with a beta-silocarbocation. Let me draw my red arrow here. That's a good enough leaving group. Could you use a tosylate? Probably. That's a little bit too powerful as a leaving group. Maybe you don't get as much control. But this will make a beta-silocarbocation, and then you'll still have this trifluoroacetate floating around that could come in and attack the silicon. Trifluoroacetate. There it is. And that can come in and add to the silicon to make a siliconate. And you know what's coming here. Then the siliconate, I'm not going to do, right? It's not an SN2. And then in a second step, you push the silicon-carbon electrons into that carbenium ion to make the olefin. And this process is an anti-elimination process, right? The oxygen leaving group has to be anti to the silicon. This is an anti-elimination. Now there's another way you can do the Peterson olefination that gives you the opposite stereochemistry. You couldn't have guessed this. You would never, there's nothing we have told you that would have made you guess that you could have done this process. The other alternative way to do a Peterson olefination is to deprotonate, to leave alkoxide anions. And the more naked the alkoxide, the better. So, right, the bond of potassium hydride is super duper basic. That bond, you can use that H potassium bond to rip off the proton from alcohols and generate hydrogen gas. It's irreversible. So you get amazing, and the potassium is not good at coordinating to this O minus. So here's this O minus, and potassium's not good at coordinating to this, but look at that right next door. I probably didn't mention this, or maybe I mentioned it 50 times, I don't remember. Oxygen loves silicon. Man, that is sweet love. And it is not as good as the fluoride anion, I get that, but oxygen loves silicon. And when you're done with all your reactions with silicon, there's usually going to be an oxygen-silicon bond in the byproduct. You would never have guessed that the oxygen, that O minus, that has nothing else to do, can attack this TMS group from the side. Not anti-paraplanar or to generate a trigonal bipyramidal that you're used to, but where the oxygen attacks it on the side. And all the bonds to silicon are now nucleophilic. And so we can now pop out a siloxide anion. Here's the arrow pushing we do for that. To make our siloxide leaving group. And now this elimination is a syn elimination. The silicon and the oxygen leave from the same face. So you end up with a different stereochemistry. This would be a syn elimination where the silicon and the oxygen are aligned on the same face during the elimination process. That's a syn elimination. So starting from the same starting material, we can either get, I don't know why I put I in the elimination abbreviation. There we go. Syn elimination versus anti. You can do this by turning the OH into a positive, some sort of a great leaving group, trifluoroacetate, tosylate. In theory, you could protonate it. Or you can make an alkoxide O minus that swings around and attacks the silicon, and the oxygen and the silicon leave from the same side. Okay, so powerful elimination processes using silicon carbon bonds instead of HC bonds. Right? Who would have guessed that? Well, is there anything that's more nucleophilic than a siliconate carbon bond? Sure there is. So it's funny because I look at the introductory organic text that we teach out of, and they show examples where they talk about making these Grignard reagents that have alkoxy groups, beta, I'm not doing a good job of, alkoxy groups, beta to a Grignard. And you can't actually use reagents like that. They're not usable. Because the second you try to make a Grignard reagent, I don't know if you remember, but the way you make Grignard reagents is you take alkyl bromides, you take alkyl chlorides, you take alkyl iodides, and you add magnesium metal. And the magnesium, we're not going to talk about the mechanisms for making this bond here, but you end up with a Grignard reagent, a carbon-magnesium bond, and that bond is nucleophilic. Just like carbon-lithium bonds are nucleophilic, you make a carbon bond to anything over here on this side of the periodic table. Carbon lithium, carbon sodium, carbon potassium, that would be insane. Carbon magnesium, those bonds are going to be nucleophilic. And so guess what's going to happen if you make this nucleophilic bond beta to an alkoxide? Well, it's going to push that out. So if your goal here is to synthesize ethylene gas, well then you'd be doing great there. Unfortunately, there's nothing else you can do with that except synthesize ethylene gas. So Grignard reagents, alkylithium reagents are not stable when they are beta to ethers, beta to esters. They will fragment apart. That nucleophilic bond will push out the alkoxy leaving group. There's other metals that you can use, sodium, zinc, that make things like Grignard reagents. Here's an example where somebody wanted to fragment this ring open, and they use sodium. We've never talked about making alkyl sodium reagents. They're way too basic. They're not controlled like alkyl lithiums or alkyl bromides. But here's where somebody didn't want to do anything useful, and so they did kind of like the equivalent. You could also do this with lithium, lithium metal if you wanted. But it doesn't matter whether you make an alkyl lithium or an alkyl sodium species, right? It's the second you make this type of species where you have an alkyl metal bond, alkyl lithium, Grignard reagent, alkyl sodium here. That's going to push that leaving group right out. There'd be no chance to do anything with that, right? That's going to open that up, and you'll end up with this fragmented open ring that has an olefin at the end. That could be useful, and some people have used that as a way to have an alkoxide or an alcohol 3 carbons away from a CC double bond. You know, this type of chemistry has also been used in protecting groups. People are always looking for ways that they can protect amines and then put in some fancy reagent and trigger the release of the protecting group for the amine. Here's an example of something called a trichloroethoxycarbonyl. I've misspelled that. It should be trichloroethoxycarbonyl. Sorry about that. A TROC protecting group. And instead of a carbon-silicon bond here, look what they've done. Instead of a carbon-silicon bond right here, they've got a carbon-chlorine bond. They've got 3 of them just to make sure that this works. So they don't have and that's not a nucleophilic bond. There's nothing about that that's nucleophilic. But if you made a Grignard reagent out of that and added magnesium, that would be nucleophilic. Now, they don't do magnesium in this case. They do zinc as the more common version. It's just like magnesium. Like you could make a magnesium chloride, make a magnesium insert into there. And in this case, you can make a zinc insert into there to make a nucleophilic carbon-zinc bond. Not quite as nucleophilic as a Grignard reagent type bond. Let me go ahead and draw that, what that would look like if you did, this would be called oxidative addition if you were doing inorganic chemistry. But it's like making a Grignard reagent. And that bond, that alkyl zinc bond, boy, that's the worst looking chloride. Let me try to fix that awful looking chloride there. And that alkyl zinc bond is nucleophilic. And it's going to push out this leaving group just like that siliconate bond did. I'm going to go ahead and draw that out. So that trichloroethoxycarbonyl group will hang out. You can do all kinds of chemistry here, and you don't have to worry. As long as you got that carbonyl group on there, you don't have to worry about this lone pair doing anything. That lone pair is dead, right? It's dead. It's not going to do anything because there's a carbonyl next door. But as soon as you take off this group, right, the intermediate that we generate here would look like this. You'd initially have this carbamate anion. I've run out of time here. I'm sorry. And then in the end, you end up with not ethylene, but dichloroethylene. And you end up with carbon dioxide floating around. And you've got your free amine. Right, those are examples of leaving groups. We are almost done with eliminations. We'll finish that up when we come back on Monday. So, boy, these elimination reactions that are like E2, right, you got to have the right bond alignment. So try to be good at recognizing when you can adopt anti-paraplanar relationships.